everyone. In the previous introductory video on COVID analytics, I discussed the layout of the software and how you can manipulate the various control here to get a better or fit against the data and how you can control the appearance. Now, in this video, I should like to take some time out to discuss the actual modeling methodology behind the computation. Now, as you can see here, it says COVID analytics, non-homogeneous SIRD epidemics dynamics. I'm going to be discussing, first of all, what do I mean by SIRD? Okay. So let's go to this Wikipedia page on compartmental models in epidemiology. Basically, the whole framework traces all the way back to the work of Kermack and McKendrick in 1927. What they did was they compartmentalized the general population into three groups. The first group is called susceptible. That means that these are the people who are not immune to the disease and therefore can become infected, but they haven't yet been infected. Okay, so it's the pristine population, but vulnerable population. The second group is called the infectious. That means people who are already infected, are currently infected, and therefore are active spreader of the disease. Okay. Finally, the third group is called recovered. These people were previously infected, but they have since become cured. They have recovered from the disease and are effectively immune. What's critical is that they're no longer spreading the disease. So they're no longer contributing to the epidemics. So this whole setup here is called the SIR modeling methodology. S obviously for susceptible, I for infectious, and R for recovered. Generally, you start off with the majority of the population being the susceptible case. If you look over here in this little diagram here, say starting with a population of nearly 1,997. Okay, you start off with this large majority of susceptible population. Then you have a very small portion, very tiny, in this case 3 being the tiny number of initially infected people. And then in the beginning you have no recovery because you only have the currently infectious, currently sick 3 people, and see what happened. Let it go from there. So what will happen is the susceptible people will decrease because they will become they'll become infected. Okay, so this blue line here, the susceptible will decrease. The infectious people will increase. But at some point, the disease will peak as people recover. So the number of recovery, which is R here, the green line here, goes up. Now, that's the original SIR model, which does not distinguish between full recovery and in fact, death. So the model that I have, for example, if you look at this SIR model, it works very well if you're not focusing on the death. In fact, if you go to, for example, this website, you see that they essentially use the SIR model because they're not focusing on the death. They're focusing just on the incidence or the infectious population. So in this case, they don't need to take into account the death part of the population. But if you are interested in capturing the death portion, then you have to go to the extension called SIRD. Okay, so that introduces a fourth group. That's the death people. Okay, so basically you, except for a very small minority, you start out being susceptible, then you become infected, and from there, 2 outcomes are possible. You either recover or you die. Okay, as you can see here, it's expressed mathematically as system of differential equation, 1 for each group. S, susceptible, has 1 differential equation. I, infected or infectious, has 1 differential equation. R, recovered, has 1, and disease has another. basically you have this rate here, which is called infection rate. Okay, infection rate here, which in this notation is represented by beta, is the rate that the infected people infects the susceptible population. So this here is how you bleed off from initially susceptible population into infected population. So this thing flows into here. Once you become infected, then again, two outcomes are possible. You become recovered. So that's this parameter here, gamma. So you goes from here, you dissipate from the originally infected into recovery. Alternatively, you have this mu here, which is the mortality rate that controls how you dissipate from infectious, not into recovery, but into death. Okay. So once again, you have four groups. This group flows into that group. This group flows into either this or that group. Okay. So in fact, that's how my cloud deployed app shows the parameters. So it has 3 parameterization as well. Now let me go to here. Okay, let's to show the dynamics, we don't have to look at the actual data. We can just look at what happened to dynamics. So this is basically a simulated case as the evolution going forward. So it's like that page, except it's not as dramatic. In this case, as much as 60-70% at some point becomes actively infectious. But in this case, it's a smaller bump. Okay, so the real model is real data is not as dramatic, but it has that kind of scenario. Now let's look at the parameter value themselves. So this is the 3 parameters that you see here, except my apology, in my implementation, because this is by no means universal, instead of calling it beta, gamma, and mu, I refer to the first parameter as alpha, A, and I refer to the second parameter as beta, B, and I refer to the third parameter as gamma. So instead of having beta, gamma, and mu, in my code or in my software, they would be referred to as alpha, beta, and gamma. So you can see them here. Now, of course, the value of alpha, beta, and gamma doesn't change as a function of time. So you can see it's a constant value throughout the period. Okay. Now, if you notice, even though over here you have alpha, beta, and gamma, they don't appear on the control panels. That's because I've made the decision to switch or recast the parameterization scheme. In particular, let me go in a little bit of details in that. This is actually in my software. I made the note. Instead of working directly with alpha, beta, and gamma, I recast them as infectivity, dissipation, and fatality. Now, infectivity is the same as before, the infection rate, so nothing new there. Infectivity is alpha. But then, instead of working with beta and gamma directly, I created this intermediate parameterization called dissipation. So dissipation controls the overall rate in which the infectious or infected population cease to become spreader of the epidemics. But once you dissipate, then you have this parameter fatality that controls whether or not it ends up in a happy scenario of full recovery or it ends up in death or disease. Okay, so the mortality then, the original infectivity is as before, alpha, right? Now the recovery rate then becomes infectivity multiplied by dissipation multiplied by 1 minus fatality. The mortality rate then is, once again, you start with infectivity multiplied by dissipation rate and that portion which is multiplied by fatality. Okay, so in this case, you can set up dissipation and fatality to be a bounded parameter. So basically, it maxes out at 1. It's constrained to be less than 1. the advantage, the mapping between alpha, beta, and gamma and infectivity, dissipation, fatality is 1-to-1. So you're not getting any additional information. But the advantage of doing it this way is that once you have this parameter, dissipation, it stands out as the most critical parameter. And in fact, if you take 1 divided by dissipation, it corresponds to the basic reproduction number. This is the key epidemics severity case monitoring statistics. So by recasting the parameterization this way, dissipation stands out, okay, as 1 over basic reproduction number. Okay. So let's see how this happens in practice. So here, the infectivity or infection rate is controlled by this slider here as before. Okay, here you have the dissipation rate. Once again, it acts the same way as 1 over basic reproduction number. So if it's very high, then the epidemics is not that severe. But if it's very low, okay, for example, I put in 0.5. That means 1 over 0.5 or 2 is the value of the basic reproduction number. Let's see what happens. Okay, it's a bit, see, it becomes immediately more severe. So it barely reaches the before. Now it's as much as 1/4 of a population at one point become currently infectious at one point. Now, if I lower the dissipation rate a little bit more, say 0.3, say 0.25, okay, that means the basic reproduction number becomes 4. So you can see this is quite severe. And in fact, under this scenario, all the susceptible people become infected. Virtually all of them become infected. Okay, so that's the parameterization. So right now, aside from the better intuition, what I've implemented is basically the SIRD framework. Okay. Finally, let me end this video by introducing my own extension to this setup, which is this. It's motivated by the observation of the health worker. They would notice that over time, this parameterization, this infectivity or dissipation rate or fatality is not constant. It can get worse or it can get better. Now, I'm thinking in terms of improvement. So it gets better. How can you make the situation better? Obviously, if you introduce a mitigation measure like social distancing, or better use more availability of face masks and hand washing and so forth, maybe you can reduce the infectivity rate over time. Okay, so instead of being a constant here, you can make it lower over time. So I introduced additional parameter called the time to improve. Okay, so this would be like, how long would it take for the health system or the health policy to cut infectivity by half? So if I, for example, I click here 300, say 180, that means it would take 180 days from the beginning of the epidemics to halve the infectivity rate. Okay, so you lower that by half. Okay, likewise, if you can have better testing program, you can sooner isolate the infected people. You can treat them sooner, and you can have them dissipated from being the infectious portion sooner. So let's say it takes you 120 days, okay, to increase. In this case, you're not trying to decrease, you're trying to increase. You're trying to increase by half or 50%. So let's do that. Okay. So dissipation rate goes up by 50% in a matter of 120 days. So once again, you're improving the situation. Likewise, as better treatment modalities become available, you get lessons learned about how to treat the COVID patient. For example, pronate them on their back or face down, for example, might help improve the death count, to lower the fatality. So let's say in 30 days time, you manage to lower the fatality rate by half. Okay. So this is the additional parameterization. All this goes to improve the situation. Now, in my original setting, let's say go to the world, I have kept all this improvement at infinity. In other words, it goes back to the time constant parameterization. How long does it take to improve infectivity by 50%? Infinity, so it doesn't improve. Okay. Now, mathematically, let me just go back a little bit. That means you're making all this coefficient function of time. So effectively, you've turned, it's quite simple, you've turned from homogeneous system of equation into non-homogeneous system of differential equation. Okay, but once again, for the data fit, I have not allowed this to happen in the fit. So in this case, say you go to Thailand again, or any other country. If you go to reset parameter, show the original data, right? All this is based on infinity being the number of days it takes to improve, because there's no improvement. But certainly you can fiddle around, say, what would happen? What would happen if we had been able to improve, okay, the infectivity? What would have happened if we had been able to improve the dissipation? In this case, the result can be quite dramatic. Okay, so once again, in the fitting scenario, I leave it at infinity, but you can do scenario analysis. What would have happened if you had been able to improve the system? And in some case, you might actually get a better fit, actually, because the reality is, in some countries, the government or the state and the health system has been active in actively trying to improve infectivity, dissipation, and fatality. Okay, so that's all for now. I hope that's been useful and intuitive. And once again, you go to this URL and you can play with this model for free. You don't have to download anything. It's on Mathematica's computational intelligence cloud deployment platform. Okay, thank you and goodbye.